Welcome to Class 3. By now you should have subscribed to this channel to support our journey through data sciences and SAP. In this class, we are going to use only ABAP, and showcase the linear algebra class, with the support for complex spaces and eigenspaces. I wrote this code initially in 1978 using assembler on the IBM/370 and just a few months ago ran it again using my System Z emulator running Linux and SOS. As such, it was a good candidate for showcasing now. I have chosen to do a demo on the power method of calculating eigenvectors and eigenvalues. The code uses extensively macros to speed up the process, although it seems fast as it is. The first series of macros are meant to expedite the creation of objects from class ZCL_matrix and ZCL_vector. I wrote this code initially in 1978 using assembler on the IBM/370 and just a few months ago ran it again using my System Z emulator running Linux and SOS. Some macros call inner macros with the more generic parameters, but as seen for the first statement, it is a wrapper around an initialization of a controlling variable and a while loop bound by it. The infer macro adds or subtracts one from the controlling variable and injects a end while command. The next block of macros initialize classes and dereferences into a field symbol. For each class I prepared macros to reduce the coding effort. Since ABAP, for some bizarre reasons, do not have a for loop statement in its grammar, I added a macros to simulate a for each. In it, I passed a control variable, the starting and ending values of the binding process from the for each to the end for. The algorithm is easy to be implemented and on its core, it reorthogonizes vectors and then compute new ones until there is a convergence based on a small epsilon constant, or it exhausts the maximum binding value with the control variable. At the end of the while statement I placed a size subric of 8 before testing for convergence, and if so, clear the return code. The remainder of the logic deals with the sign of the eigenvalue and its placement on a vector object, since the eigenvectors were already produced by the reorthogonalization step. Another series of methods are leveraged to run specialized code for matrix to vector transformation, scalar multiplication of vectors and other methods. I have chosen not to leverage the generalized versions on classes ZCL_vector and ZCL_matrix for two reasons. First, I did not want to closely tie the implementation of eigenspace objects with the latter two, and second, I wanted to create a secondary method that runs almost all support methods by macros to make the code more efficient. The macro-based method would be tested in the next class when I demo the complex number processes created. At the tail end of the code, I added a move into the eigenvalue vector, which contains one eigenvalue per dimension corresponding to the equivalent eigenvector returned by the matrix. As usual, I defaulted the return as a column-based matrix where each column hosts an eigenvector, but provided a Boolean flag to transpose the eigenvector matrix into row-based representation. This is the bulk of the code needed for data scientists to perform AI and ML solutions in ABAP leveraging the eigenspace support. It is unusual for data scientists to care for complex numbers, but in case eigenvalues are complex, the solution demo does not provide the necessary support for these cases. However, there is a similar method to return eigenvalues and eigenvectors using complex numbers represented via sines and cosines of multidimensional cubes. I am now running the same test engine created before with a 4x4 matrix whose values I calculated the eigenvectors and eigenvalues using the Z/OS original assembler code. Upon entry I show that matrix A is filled whereas the importing objects aren't. The beginning of the test code was left untouched and I only manually created the rows of the A matrix with the known values. A breakpoint was set on the call to the method and my setup was done. It is time to run the test program. As expected, the breakpoint activates and I changed the top tool from the ABAP stack trace to the table display and made sure my matrix A was correctly done, and the importing parameters set to initial values. The reason for passing initial pointers to the method are twofold. First, to reduce heap allocation of objects at the receiving end when their internal representations are only valid at the return of the method. Second, ABAP does not allow two variables to be returned from a method, which is quite common in Python. At the method side of the equation, the usage of heap objects is limited to the bare minimum, which is quite different approach from the objects themselves, matrix and vector. This was mentioned before when I explained the support methods used rather than the generic ones from the two object classes. Unfortunately, the display resolution from the remote desktop is super bad, making the real estate for the table contents as well as local variables a pricey commodity. I'm recording this video on my Mac and connecting to the S/4HANA system, which runs on a Docker image at the Windows Server 2022. Rather than monkey around NAT tables and Docker IP configurations, I rather use the remote desktop to access both Eclipse and SAP GUI. I am now going to run the method and check the results by jockeying around the pricey real estate and trying to demo that indeed the eigenvalues and eigenvectors were calculated. As explained before, I returned the eigenvalues on a vector object and each corresponding eigenvectors on each of the 4 columns of the matrix. Well, I can almost guarantee that some of y'all would be saying, it is returning a bunch of numbers, indeed. But how do we know the code really works and the eigenvalues and eigenvectors are real things instead of a bunch of random values? Predicting the ever-inquisitive minds, I shown the original matrix, and one can run an online program, there are plenty to choose from, and check the 4 eigenvalues and each of the eigenvectors for accuracy. I demoed this code not only to show that complex calculations are possible in ABAP if one uses decfloat34 representation, plus minus e to the power of 6600 or near it, but also that the code runs just as fast as Python's. I am not going to show the runtimes, but suffice to say they are not far off one from another. In my next video I will showcase the support for sigmoid functions, as well as various kinds of other functions used to do gradient descent approaches to models. The first module ends with a demo of a model running in ABAP and training using the same datasets given to Python via pandas. I wanted to use some real S/4HANA table values, but it is not really necessary. Suffice to say, any clean dataset would work. In hindsight, I should have run the code without the beak point to show how fast it works, but y'all could derive the same conclusion by noticing how fast the method returned. Until next class, please do subscribe to the channel, and give me a like to boost my ego with at least a few ABAP souls that like complex coding.